Okay, so we're going to talk a little bit about L'Hopital's rule. And this is the formal statement of L'Hopital's rule. There are a few things I want to take a look at. So first off, you need that your functions are both differentiable, close to x equal to a. That's going to be important because we're doing the limit as x goes to a. And we need for our derivative not to be 0 of our denominator, and that's simply so we don't have division by 0 as we evaluate our limit. And then really this part here is saying that we have two different scenarios where we could use L'Hopital's rule. The first one is that both of our functions are going to go to 0, and we're looking at the ratio of the two of them. So really that's saying, okay, if you have either 0 over 0 or you have the second case where both of them are infinite, that's going to give you infinity over infinity. Okay, so if you have 0 over 0 or infinity over infinity, then you will be able to apply L'Hopital's rule, and L'Hopital's rule says that the limit of your ratio of two functions, f of x over g of x, if that's 0 over 0 or infinity over infinity, then you can apply L'Hopital's rule, and really you're just going to be comparing their individual derivatives. Okay, you compare the derivative of f of x to the derivative of g of x. You're comparing their rates of growth. Okay, and typically we will sort of have some way of representing that we have used L'Hopital's rule. Here I'm going to put just an h on my equality. Now really you don't want to memorize this whole rule. Okay, the basic idea behind L'Hopital's rule is that anytime we have these two indeterminate forms, one or the other, we can use L'Hopital's rule, and L'Hopital's rule just says this right here. Okay, the limit of the ratio will be equal to the limit of the ratio of their derivatives. Okay, so before we do some examples, let's take a look at not only 0 over 0 and infinity over infinity, because those are two indeterminate forms, but let's take a look also at the other indeterminate forms. So you should remember 7 indeterminate forms. These are the two that we just saw. We're going to group them together, 0 over 0 and infinity over infinity. 0 times infinity you also saw early on in Cal 1, and then probably shortly after that you saw infinity minus infinity. And then towards the end of the course you would have seen these three exponential indeterminate forms. Okay, and these are sort of always grouped together. Now, for L'Hopital's rule, I'm going to show you essentially how to do these two groups, okay? Because L'Hopital's rule can be used for all of them, even though directly you can only use L'Hopital's rule when you have 0 over 0 and infinity over infinity, okay? So I'll show you just sort of a brief idea of how we're going to go about doing that. If we have 0 over 0 or infinity over infinity, okay, the basic idea is that we can use L'Hopital's rule. Now, if you have 0 times infinity, our goal is going to be to eventually use L'Hopital's rule. However, how do you get there? Well, what we're going to do is a little bit of algebra. We're going to take 0 times infinity, we're going to turn it into either 0 over 0 or into infinity divided by infinity, and then we just finish off using L'Hopital's rule. So fine, those ones won't be too bad. And then the last thing is, how do we deal with these exponential indeterminate forms? Well, we deal with them very much in the same way. If you have either one of these exponential indeterminate forms, then what you're going to do is you're going to manipulate them, you're going to turn them into 0 times infinity, and now we know how to deal with 0 times infinity. So that's going to cover 6 of the 7 indeterminate forms, and the reason that I've left this indeterminate form out is because it's not sort of handled in the same systematic way. You can't go through the same process to get to L'Hopital's rule every time. Based on the type of question that you're dealing with, infinity minus infinity is going to require a slightly different technique every time. Okay, so we're not going to focus on that in this video. We're going to focus on the other 6 of the 7 indeterminate forms. Okay, so let's take a look at a intro example for now. Limit as x approaches 1, ln of x over x minus 1. So the first thing we try to do is try to do our direct substitution. However, this here is going to go to 0 as x approaches 1, and ln of x itself also approaches 0, so we do start off here with the indeterminate form 0 over 0, and you always want to check to make sure that you do have that indeterminate form before using L'Hopital's rule. Okay, so now we do limit as x goes to 1. We're going to do individually their derivatives. So we have the derivative of ln of x, and we have the derivative of x minus 1, which is just 1. And now this limit is pretty much done because the denominator is constant. It just approaches 1, and the numerator is going to be approaching 1 divided by 1, which is 1. So this whole thing altogether is just going to approach 1 over 1. It's going to approach 1. And it's a limit that exists, it's convergent. Okay, so that's the basic idea, guys, behind L'Hopital's rule. Let's take a look at another example. Okay, so this one's only just a little bit different. When we have x approaching infinity, this time we're going to get that the numerator approaches infinity, the denominator approaches infinity. So we do have an indeterminate form, and we have infinity over infinity. So we're able to use L'Hopital's rule. So we are going to do that. We can do the derivative of the numerator and the denominator separately. In the numerator, the derivative of e to the x is e to the x, and in the denominator, the derivative of x squared is 2x. So fine. Now again, we're going to try to do our direct substitution, see what happens with these individual functions. E to the x is still going to approach infinity, and actually so is 2 times x. So really, we applied L'Hopital's rule, but we haven't managed to get rid of the indeterminate form. We still have infinity divided by infinity. So you might think to yourself, okay, this isn't working, except what can you do when you have infinity over infinity? Well, you can just use L'Hopital's rule again. And there's no limit to the number of times that you can use L'Hopital's rule, but I would say sort of as a general guide, if you've done it 3 times and it really doesn't seem to be working, you might be doing it sort of the wrong way. So let's do it again. We have here the derivative in the numerator and now the derivative in the denominator. And you'll recognize that even though my numerator still goes to infinity, my denominator does not. And so this limit is pretty much done. We have our numerator increases without bound, but our denominator does not. This limit is positive infinity. This limit does not exist. Okay, so that's multiple uses of L'Hopital's rule, guys. Next time, let's take a look at a slightly different indeterminate form. Not 0 over 0, not infinity over infinity. We're going to look at 0 times infinity. Okay, so for this one, again, we try to see what happens as x approaches infinity. This time we have the square root of x. That's going to approach positive infinity. And we have e to the negative x over 2, which is going to approach, well, it's going to go to e to the negative infinity, which you have to recognize that's actually going to go to 0. And so we have the product of the two of them, which means we do actually have an indeterminate form 0 multiplied by infinity. And so we're going to have to deal with that indeterminate form. Now, how do you deal with 0 times infinity? Well, like we saw earlier on in the video, we're going to turn this into either 0 over 0 indeterminate form or infinity over infinity. And it's the same thing every time. Anytime we have 0 times infinity, we do this. Why do we do it? Because then as soon as we do that, we can use L'Hopital's rule and hopefully finish off the question. Okay, so let's take a look at our two functions. We want to choose one of them, and we're going to sort of artificially put it into the denominator. So let's go back up. We have limit as x approaches infinity, and we could choose either to deal with root x and put into the denominator, or e to the negative x over 2. But you should notice that e to the negative x over 2, because it has a negative exponent, it's essentially already in the denominator, so it's not really going to make our question any more difficult. We can rewrite our function like this. And these two things are still exactly equal to each other. Okay, so we haven't changed our limit at all, we've just rewritten it algebraically. So now we did that because if we check our limits again as x goes to infinity, the numerator goes to infinity and so does the denominator. So we have now taken our indeterminate form of 0 times infinity, and we have turned it into infinity over infinity. So then the next step is just to use L'Hopital's rule. Okay, so that's what we're going to do. And this one shouldn't be too bad. We can do the derivatives separately. This in the numerator is just x to the 1/2. So when we do the derivative, we get 1/2 x to the minus 1/2 divided by the derivative of e to the x over 2, which is going to be e to the x over 2 times the derivative of x over 2, which is just going to be 1/2. Now let's clean this up a bit. So after you do L'Hopital's rule, okay, don't try to do direct substitution again. Always just try to simplify it, then try to do your direct substitution afterwards and see what you get. So now we got rid of the 1/2. Really, what we end up with is the limit as x approaches infinity. We have here, we could rewrite it, 1 over the square root of x times e to the x over 2. And now let's take a look actually at what happens as x goes to infinity. This term goes to infinity, and so does this one. So you have to ask yourself, if we have infinity times infinity, is that an indeterminate form? And it is not. So this is actually just going to go to 1 over an ever increasing number. This whole thing is just going to go to 0. That limit exists. Okay. So the main idea with this one, okay, that you have to understand is whenever you have 0 times infinity, you're always going to turn it into one of these two indeterminate forms, and your reason you're doing that is so that you can use L'Hopital's rule. Okay, so now I'm going to do one example where we look at the exponential indeterminate forms, and you'll see that again we go through a very similar process as we did right here.